This lecture is on magnetic materials, and there are materials that are considered soft magnetic and hard magnetic. We'll learn about those a little bit more. One thing that would be interesting is if we have something that's not magnetized, we could possibly magnetize it by rubbing it in a certain direction with a magnetized item. These materials are called ferromagnetic, so they can gain a magnetic field by rubbing them with something that is magnetized. But how does that happen exactly? Let's write this down first here. The soft ferromagnetic materials are things that are that have to be magnetized in that sort of way where we rub them with something that is magnetized. But there is also hard ferromagnetic materials, which are materials that are just naturally in a magnetized state, and they retain that magnetic property over a longer period of time. Soft ferromagnetic materials will eventually lose their magnetized state. So what's happening with a soft ferromagnetic material? Well, what's happening is we're organizing the magnetic dipoles that exist inside the material. So if we consider a magnetic dipole, let's say we have little sticks of iron inside of a material, and they could be oriented in a whole bunch of different ways. Some of them could be right, some could be left, some could be up, down, in or out at different angles. But these little sticks would all be kind of randomly oriented. If they're oriented in a random direction, then the entire material will not be magnetized. But if we rub them with something that's magnetized, we'll start to force those dipoles, which are really just little, you can think of them as little magnetic vectors, little arrows, or you can consider them to be basically just a two-dimensional kind of figure. If we arrange those dipoles in one direction, we can end up having a north and a south pole created, and then we'll have a magnetic flow outside of the magnet as well, and that will create the magnetic field. So we magnetize a ferromagnetic material by orienting its dipoles in one direction, all in one direction. We could reach the maximum number of aligned dipoles, and that's a situation we call magnetic saturation. That's when a material is at its maximum magnetized strength. It can't be magnetized any further. So let's write this down here. Dipoles are atoms of ferromagnetic substances that act like tiny little magnets. When we have a whole group of them, we call that the magnetic domain. And if we can get them all to line up, then we end up having a magnetized material. You may have thought of this, if we have a bar magnet and we cut it in half, do we end up having just a north pole and a south pole? Well, what actually would happen is a new south pole and north pole would be created when we break a magnet. Because once that's broken, the dipoles at the south pole, the new created south pole, will now I guess you could say they were attracted to the new north pole, so the magnet would kind of be looking at sticking together. But if you separate them far enough, you can then point the south pole at the south pole, which would repel each other. So that's what happens when we break a magnet in half, a bar magnet specifically. Why does a permanent magnet brought near an iron nail cause the nail to become temporarily become a magnet? So the field of the permanent magnet causes the dipoles in the iron nail to align momentarily, making the nail a temporary magnet. So that's how we can the dipoles in a nail that is ferromagnetic. We can turn that nail into a magnet by putting it next to a strong magnetic field. This is a process that we call magnetic induction. So we induce a magnetic state into something that is normally not magnetic. So here's magnetic induction, and I'd like you to copy down the image. So before we have randomly oriented dipoles, and after we have dipoles oriented in one direction. Here's a did you know. It says if a piece of iron is held on Earth's magnetic field and its atoms are are agitated either by heating or by mechanical vibration, its dipoles will align. This is we see this as well if we have iron filings in a magnetic field on a sheet of paper. The iron filings might not be oriented in the way the magnetic field is directed, but if you start hitting the piece of paper, they'll start to orient. So as we agitate something or move something, it'll start to become magnetized. Steel columns and beams used in construction are usually found to be magnetized. Steel hulls of ships and railroad tracks also are magnetized by the Earth's magnetic field. If something goes from a magnetic state to a non-magnetic state, we call it, we say it's being demagnetized. So because those little dipoles are really atoms, we could have things that make them move, like thermal energy. If they're heated, they tend to move around, and as they move around, they might move out of their orientation, which would demagnetize something. You could physically agitate something as well to demagnetize it. If it's not in a magnetic field in the first place, and you hit a bar magnet really hard multiple times, you could deorient the dipoles, and it could be demagnetized. So here's some methods of demagnetization and the definition of demagnetization in terms of magnetic dipoles. One way that we prevent demagnetization is by placing an iron bar called a keeper across a U-shaped magnet. This slows down the demagnetization because it creates a full loop, and the magnet is constantly working on magnetizing that soft iron. We've already talked about this. How can you magnetize a screwdriver? If you rub it with a magnet in one direction, it'll be magnetized in that direction. If we drop the screwdriver or heat it, it would lose its magnetism because its dipoles would be randomly aligned again. The lodestone discovered in Magnesia was a naturally magnetized substance. Describe the process whereby the magnetism likely occurred. It says, hint, volcanic eruptions are common geological events. So, it says here, lava is ejected. Before the lava cools, the dipoles in the molten rock align themselves with Earth's magnetic field. The lava cools, and then we have naturally magnetized substances that are created.